Okay, today we're going to talk about related rates. And what related rates is it's the relationship between how different parts of an object are changing over time. So, for example, if you're blowing up a balloon, it's the relationship between how the volume is changing and how the radius is changing at the same time, because they're not necessarily changing at the exact same rate. Okay, so let's use the balloon example here. Air is being pumped into a spherical balloon at a rate of 4 pi inches cubed per minute. Determine how the radius is changing when the radius is 2 inches. And then we're given the volume of the sphere formula. Okay, so I want to focus in on the fact that air is being pumped into a spherical balloon at a rate of 4 pi inches cubed per minute. Okay, what this means in terms of this problem is that the rate of change of the volume is 4 pi inches cubed per minute. So the way that we're going to denote that is we're going to say that dV dt, which is the derivative of the volume with respect to time, or the rate of change of the volume, equals 4 pi. And we want to determine how the radius is changing when the radius is 2 inches. So if we're talking about how the radius is changing, then we're looking for the rate of change of the radius, or dr dt. So the derivative of the radius with respect to time, because the derivative is the same thing as rate of change. So we're looking for dr dt when the radius is equal to 2. All right, and then we're given the volume formula for the sphere. So what we have to do is we have to take the derivative of this equation right here. And we're going to always take the derivative with respect to time. Remember that we can take the derivative with respect to any variable, but for all of these related rates problems, we're going to take the derivative with respect to time. So the derivative of v with respect to time is dv dt. And the derivative of 4/3 pi r cubed, the 4/3 pi is just a coefficient, so it's going to stay the same. And then we're going to take the derivative of r cubed. So the exponent of 3 is going to come down in front, and that will actually cancel with the 3 in the denominator there. So I have 4 pi r squared, and then we just took the derivative of r. So I have to put in dr dt to denote that I've taken the derivative of r with respect to time. So anytime you take the derivative of a variable, you're going to stick in that variable over dt. And now I just need to make the numerical substitutions for what was given to me and solve for what I'm looking for. So it was given to me that dv dt is 4 pi. So I'm going to put 4 pi in for dv dt. And I'm looking for dr dt when r is equal to 2. So 2 squared times dr dt. And I will usually let you use your calculator on problems like these, but even these ones in the notes we really don't need the calculator for. If you can look at this a couple different ways. We see a 4 pi on both sides of the equal sign. We can divide both sides by 4 pi, and we're left with 1 on the left, and then 4 dr dt on the right. So to solve for dr dt, I get that dr dt is equal to 1/4. And you always have to label your units here. Dr dt represents the rate of change of the radius with respect to time. So if the volume was changing, if the units of the volume changing was inches cubed per minute, volume is a cubic measurement. Radius is just a linear measurement, so this is just inches per minute. And that's your answer. All right, let's look at the next one. All right, water is dripping out of an inverted cone at a rate of 2 feet cubed per minute. The cone has an altitude of 10 feet and a base with a diameter of 6 feet. Determine how fast the height of the water is changing when the height is 4 feet. Okay, so the first thing that jumps out at me is I'm trying to find how fast the height of the water is changing. So I'm looking for the rate of change of the height. So what I am looking for is dH dt. And as soon as I figure out what I'm looking for, I'm going to write it down. So dH dt is what I'm looking for. And I want to find dH dt when the height is 4, so when h is 4. Then I'm also given another rate, and that is the fact that the water is dripping out of a cone at a rate of 2 feet cubed per minute. So that measurement of water is the volume of the water. And we know that because that's how you would measure the inside of a cone, is in terms of volume, and also because of the units on this, it's in feet cubed per minute. One thing you need to be a little bit careful with, so this is the rate of volume, so it's dV dt. If the water is coming out of the cone at a rate of 2 feet cubed per minute, then dV dt is going to equal -2, because the volume is decreasing, so therefore its rate of change is negative. Okay, so we're going to draw a diagram and label it appropriately. So I know that the full height is 10, and it says that it has a diameter of 6, but we only use radius. So it has a radius of 3. But we're interested in here at some point in time when the height is not necessarily 10. So then, and hopefully you remember this from an after party not too long ago, so at whatever level the water is, I'm going to call that H, and then I'm going to call this little segment R, the radius of the surface of the water. Okay, so the next step then is to write an equation for the volume of the cone involving only the variable of the rate to be determined. And we need to look for geometric relationships here. So the variable of the rate to be determined, we're looking for the rate of change of the height. So that means that this entire problem needs to be just in terms of h. Well, we're given that the volume of the cone is the area 1/3 times the area of the base times the height. Well, the base of a cone is a circle, so the volume of a cone is 1/3 pi r squared h. But I want to rewrite this equation just in terms of the variable of the rate to be determined, and that would be my height. So I need to get rid of this r that's in my volume equation and rewrite it in terms of h. Okay, so that's where these geometric relationships come in, and hopefully you remember this from a very recent after party. So if I redraw these two similar triangles that I've created here, then the height of the big triangle was 10, and that side is 3, and then the height of the little triangle is h, and that side is r. So I have two similar triangles right here, and I can write a proportion. You could do 3/10 equals r over h. So if I want to get rid of the r over here, then I need to solve this proportional relationship for r. So if I cross multiply, I get 10r equals 3h. So therefore r equals 3/10 h. And now I can plug that back into my volume formula. So volume is 1/3 pi. Be really careful here. R is the quantity 3/10 h. But in the equation, I need to square it. So I need to square the entire quantity 3/10 h. And then I've got the other original h. All right, we are going to eventually always take the derivative on these problems, so I need to simplify this before I can take the derivative. When you square 3/10, you are going to get 9/100. So we have 9/100 h squared times the other h. And I would suggest simplifying this and reducing it. 3 will go into 9 3 times. So I end up with 3/100 pi h cubed. So that's the volume in terms of just one variable. And that was the whole point of the after party that you did recently, was to get you in the habit of rewriting some of these equations, volume formulas and things like that in terms of just one variable. All right, so now we can get down to the business of the calculus part of it and finding the relationship between these different rates. So we're supposed to take the derivative with respect to time. So if this is my volume, I want to take the derivative of that. So the derivative of v is going to be dv dt, derivative of v with respect to time. And then the 3/100ths pi is all a coefficient. So I just need to take the derivative of h to the third. So the 3 is going to come down in front. That's going to give me 9/100ths pi, h squared. And because I'm taking the derivative with respect to time, I need to write dh dt. Okay, I had to move the page down, so I recopied all of the important information here. All right, so now we just need to make the numerical substitutions that are unique to the rate that's being requested. So we are trying to find dh dt, and I just need to plug in all the other parts that were given to me. So dv dt we know is -2 equals 9 pi over 100. I'm going to plug in an h. I'm going to plug in 4 for h, so 4 squared is 16. And then I'm looking for dh dt. All right, we are going to do this without a calculator. Don't freak out. I definitely suggest reducing before you try multiplying. There's no reason to multiply 9 times 16 because 16 over 100 can easily be reduced. All right, 16 and 100 are both divisible by 4. So if you divide them both by 4, 100 divided by 4 is 25, and 16 divided by 4 is 4. So we have -2 equals, and then we have 9 pi times 4, so 36 pi over 25 dh dt. I definitely suggest that you get in the habit of writing your pi's up on top of the fraction instead of kind of out on the middle. You can see that on part C, I kind of wrote it out on the middle, but in just a minute, it will be to your benefit to have that pi up there in the numerator. So to solve for dh dt, I essentially need to multiply both sides by 25 over 36 pi. So when I multiply both sides by 25 over 36 pi, I'm going to get -50 over 36 pi. And you've got to be very, very careful that that pi ends up there in the denominator the way that it should be. All right, and then the last step is just to fill in our units. The rate of change of the volume was feet cubed per minute. So the rate of change of the height, which is a linear measurement, is just going to be in feet per minute. And that's as hard as these problems get. And what makes this problem more challenging than the first one is the fact that you just had to relate your height and radius together and write that proportion. But you're always doing the exact same thing. You're rewriting the formula in terms of just one variable by finding some sort of geometric relationship and then taking the derivative and with respect to time and plugging in those known values. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? All right, I'd like for you to, on your own, write down everything that you know about this problem, to write down the rates that are given to you and also the rate that you're looking for. All right, so it says the radius is increasing at a constant rate of 1 foot per second. So that means that dr dt, or the rate of change of r with respect to t, is equal to 1. And we're looking for how the area is changing. So that's represented by dA dt when r equals 4. All right, well, if it's asking us to find the derivative of the area, then we need an equation for the area of a circle. And we all know that the area of a circle is pi r squared. All right, so we have an equation that's just in terms of one variable. So now we can take the derivative and make our substitutions. So I would like for you to pause the video and finish this problem off on your own, and then you can start it back and check your answer. All right, so when you take the derivative of your area formula, you get the rate of change of the area, or dA dt, is equal to 2 pi r dr dt. And we know that we're looking for when the radius is 4, so I plug that in, and we're told that dr dt is equal to 1, and so that equals 8 pi. Now, this time we're finding the rate of change of the area of something, and therefore area is measured in terms of a square unit. So, and we're talking about feet and seconds, so the answer is 8 pi feet squared per second. All right, and that's it.